This is Sounak, and today I'll be talking about the experimental observation of orbital Hall effect of light. This is a part of my thesis which I worked on under the supervision of Professor Nimala. Light carries three types of angular momentum. First is the spin angular momentum, which owes its origin to the circular polarization of light. This can be plus or minus 1, depending on whether it's left circularly polarized or right circularly polarized. Next, we have the intrinsic orbital angular momentum of light, which is related to the helical wavefront. This is represented by L, which is a number of intertwined helices. Then we have extrinsic orbital angular momentum, which is connected to the position of the field. Just like a spin-orbit interaction leads to the spin-Hall effect of light, orbit-orbit interaction can cause orbital Hall effect of light, where the intrinsic orbital angular momentum converts to extrinsic orbital angular momentum, leading to a shift in the vortex beam. Analytically, we can see that the partial reflected Lagrange beam is a superposition of orbital angular momentum modes L, L plus 1, and L minus 1, which is manifested as a shifted vortex. Experimentally, we try to see this orbital Hall effect of light using randomly and radially polarized vortex beams, and we use these to eliminate the effects of spin polarization and study the effects of pure orbit-orbit interactions. In both the cases, we observe a shift in the intensity distribution, which scales as the value of orbital angular momentum, which is L, and the intensity distribution shifts in opposite direction for plus and minus L. Also, we see that the shift increases with the angle of incidence. For the polarized, radially polarized case, we additionally see lobe formation. This happens because the intensity near the horizontal axis of the radially polarized beam is cut off near the Brewster's angle. Here, the shift in the intensity distribution will be now seen as an asymmetry in the lobes. The experimental results show excellent agreement with the simulations. Further, we can try to quantify the change in the phase structure as a signature of the orbital Hall effect from interference. What we do is we interfere the orbital angular momentum beam with a Gaussian beam for the total reflection case as well as the partial reflection case, and we get a fog pattern from which we extract the phase. So we see that there is a lower azimuthal phase gradient for the partial reflection case. This can be explained as the secondary contributions which arise from the L plus 1 and L minus 1 side bands. They decrease the phase gradient in comparison to the pure L phase structure. And this interferometry scheme also provides an alternative approach to study orbit-orbit interactions. So to summarize, this work demonstrates the first experimental observation of the orbital Hall effect of light, which is solely due to the orbit-orbit interactions. And we achieve this using randomly and radially polarized vortex beams. This effect is also consistent with the total angular momentum conservation. So that's the end of my presentation, and thank you for your attention.